Hello info person, this is Anton, and today we're going to be discussing this really bizarre phenomenon that was recently physically confirmed by observing something out there in outer space. And well, specifically, it's a phenomenon in regards to vacuum. And so, okay, imagine this. Imagine empty space, the absolute nothingness that represents most of the cosmos up there above the atmosphere. Back in school, we were always told that vacuum is just emptiness. But the question is it actually empty? And can it act as something physical, even though it has nothing inside? And well, as you can imagine, based on the study we're discussing today, and based on these observations, the answer seems to be yes. Under the right conditions, the empty space itself starts to behave exactly like a solid, transparent crystal. Not so different from what you see right here. And this crystal starts to bend light, split beams, and even act like a physical lens, despite once again having nothing inside. And though this might sound like science fiction or something that shouldn't happen, based on this groundbreaking study from August 5th of 2026, we now have definitive direct proof of a strange phenomenon referred to as vacuum birefringence, something you can learn more about in the link in the description. And so here, by using a fleet of telescopes on the planet and a giant radio dish in order to observe radio frequencies, approximately 15,000 light-years away from us, here a team of astronomers witnessed a very strange effect as the fabric of space itself started to do something that was predicted 90 years ago. It started to physically act like a lens. And so in this video we're going to discuss exactly how this works and what's happening here, talk about the quantum weirdness of empty space, and discuss how an extremely strong magnetic field can sometimes create very bizarre effects, but also discuss the major implications from this discovery. But in order to understand all of this, we have to start with a definition of what exactly birefringence means. Or basically, what exactly is this optical phenomenon that sometimes is also referred to as double refraction? And while normally when light passes through something transparent, like water or glass, it slows down just a little bit, with the measurement of this slowing down normally referred to as the refractive index. And for a typical material like glass, this type of index is basically the same in every direction. So it doesn't really matter how the light waves are oriented, because they'll all travel at exactly the same speed. But certain crystals, like the calcite crystals, which is what you see right here, are just a little bit different. The proper term for this is anisotropic. And basically that's because of the way that the atoms inside are arranged. They possess a very strict repeating grid that resembles something like this. And here the electrons bound to these atoms are usually held with different strengths in different directions. And while light passing through these crystals, because it's affected by these electrons, tends to be refracted differently depending on the angle. And so as the light wave, which is basically an oscillating electromagnetic field, passes through the crystal, it starts to vibrate some of these electrons, with the vibration then affecting the light. And because electrons are easier to wiggle in one direction compared to other direction, the light wave here is going to experience different refraction depending on the direction it's coming from. And while specifically we're actually talking about the orientation or polarization of the wave as opposed to the actual angle. And so when unpolarized light enters such a crystal or such a material, it gets split into two separate beams, traveling at slightly different speeds, and also taking slightly different paths. In physics, these are referred to as ordinary ray and extraordinary ray. They basically have slightly different speeds, possibly faster or slower, and can even exit the crystal at an angle, even if it entered completely straight. And so when you look through such a crystal, like in this case, you sometimes see two sets of images. Or even might see something like this. As a matter of fact, very similar principles are actually used in things like LCD crystals and for various types of scientific instruments involving optical modulation. In other words, when it comes to birefringence, it's quite well known, and there are a lot of examples on the planet. But here we're talking about physical crystals. So how exactly would vacuum produce the same? Here we're talking about space that potentially contains zero crystals, yet somehow it seems to be able to do something very similar. Which means that we now have to discuss the slightly different concept involving quantum mechanics. And so, to try to imagine this, we now have to look at the subatomic world, and specifically the quantum electrodynamics, also known as QED, where vacuum is not empty space, but is instead seen as this, a kind of a boiling soup of virtual particles that come into existence and annihilate each other almost right away. And so, according to Heisenberg's uncertainty principle, there's a fundamental limit to how precisely we can know certain pairs of physical properties at the same time. So, for example, if these two pairs are energy and time, the math tells us that here the energy becomes the uncertainty and must always be greater than or equal to a tiny constant. In this case, Planck's constant divided by 2. Okay, ignoring all the math and physics, in a nutshell what this means is that the universe itself allows the energy to be borrowed for a very short moment from the empty space itself, as long as it's returned incredibly quickly. And so because of this, pairs of virtual particles, specifically virtual electrons and positrons, are constantly popping into existence out of absolute nothingness, existing for a tiny fraction of a second, just to crash back, annihilate, and become nothing again, essentially returning their energy to the vacuum. And even though this is not something we can directly see with, for example, a microscope, their cumulative physical effect is actually visible and measurable. For instance, without this cloud of virtual particles, when it comes to the mass and charge of real particles, and specifically the standard electron, the calculations no longer work. As a matter of fact, the mass and charge of an electron calculates to be infinity if it wasn't for these virtual particles. And so here the shielding effect from the quantum vacuum is what gives elementary particles their finite observable mass and charge through the process referred to as renormalization. But all of this is just to help you understand that the cosmos and the vacuum of space is filled with this at all times. Okay, well then the next question is, so how come we don't really see this everywhere, coming from every direction? Well, that's because this effect is super weak. And only certain conditions, such as ridiculously powerful magnetic fields, can sometimes turn this boiling soup into an actual crystal-like structure. And so in a normal environment, these virtual pairs of particles pop in and out of existence in random orientations. So here the vacuum remains isotropic. It behaves the same in every direction. But by introducing ridiculously strong magnetic fields, and here we're talking about something that you can only find around magnetars, something crazy starts to happen. Electrons and positrons forces these particles to now align themselves along the magnetic field lines, despite the fact that once again they only exist for a fraction of a second. And because of this, the vacuum itself suddenly acquires a preferred direction. And that means that if some kind of a light travels through this magnetically polarized vacuum, the electric field inside of this will interact with the light differently depending on the light's orientation. And so because of this interaction, different types of polarized light will travel at different speeds through this empty space, thus creating this birefringence effect in the supermagnetic conditions. But once again, this can only happen if the magnetic field is absolutely astronomical, with the initial predictions in the QED suggesting that this can only happen in the critical threshold referred to as the Schwinger limit. It's a very big number, so I'm not gonna try to say it, but just to give you a comparison, right now in the lab on Earth, the strongest magnet we can make, or the strongest continuous magnetic field we can create, is approximately 45 Tesla in strength. And we need something that's several million times stronger than this in order to reach the Schwinger limit and start to create these effects. So once again, this can only happen around magnetars, or these very extreme neutron stars, usually about 12 kilometers across, with the density so extreme that they form some of the densest matter in the universe. And so compared to a regular star, here, this very powerful magnetic field now operates in a very small volume of space, with all of the magnetic field lines compressed tightly together. And in many cases, their magnetic field is well above the QED critical Schwinger limit, which potentially makes them a perfect location to observe this vacuum birefringence in action. And well, for many years, this is exactly what's back in 2016. Here, a team of astronomers led by Roberto Mignani used the Very Large Telescope in Chile to measure some of the faint light from a nearby quiet neutron star referred to as RxJ 1856, something that's not too far away from us at 400 light-years. As a matter of fact, this is the closest neutron star to planet Earth. And here they seem to have detected a linear polarization, which was very intriguing. It was actually a really interesting result, but because it was so far and because it was so dim, here the overall measurements were very difficult, and the overall models of the neutron star atmosphere were just a little bit uncertain, so it wasn't clear if this was a definitive result or if it was maybe some kind of a miscalculation. Which means that, in order to prove birefringence around neutron stars, researchers had to look at something that's not optical light and something that's maybe higher in energy, for example X-rays, which is exactly what this recent study from 2026 managed to achieve. And here they used a magnetar referred to as 1E1547 that's actually just a little bit unusual because it's one of only a handful of magnetars that also seems to be a persistent radial pulsar. It basically spins every 2 seconds and also contains just enough magnetic field to reach that required limit. It's actually 5 times above this limit, suggesting that it's powerful enough to crystallize vacuum. But because it emits both bright, highly polarized radio waves and X-rays, it presented scientists with a unique opportunity, which is what they did between March 26 and April 5th of 2025. Here, this large team coordinated an intense observation campaign by using NASA's X-ray Polarimetry Explorer and NICER aboard the International Space Station. This was used to observe the X-rays. And to observe the radio waves, they used the Parkes Observatory in Australia. And this was actually the first time in history scientists were able to obtain simultaneous observations from a radio and X-ray polarization of a magnetar, with the results finally analyzed, published in this study. And here the results are pretty clear. The X-ray emissions seem to be polarized by about 46%, which is the highest polarization ever detected from all magnetars observed before. And it even went up to 80% at certain rotational angles as the magnetar was spinning every 2 seconds. Okay, so what does this mean and why is this unusual? Well, if the vacuum itself is not crystallized around this neutron star, then no matter the rotation and no matter what angle you look from, the overall polarization should be almost zero, at least in certain points. But according to simulations and all of the mathematical analysis, the only way to acquire such a high polarization is basically if the vacuum itself becomes crystallized and creates these birefringence effects. And just to rephrase this again, around this magnetar, the space itself, even though it contains nothing, starts to resemble a crystal and produces very similar effects to what you're basically seeing right here. And surprisingly, the photons in this case seem to actually be affected by this anywhere from 30 to 300 stellar radii away from the neutron star, or up to about 2,000 kilometers away from the neutron star's surface. So this is not just something that's extremely small, this optical effect literally makes the neutron star resemble a massive crystal. With additional observations also discovering something referred to as vacuum resonance, which in basic terms once again confirms these quantum predictions and suggests that, depending on the energy of the photon, they're going to start producing slightly different birefringence effects. And so pretty much everything that was predicted in the QED, or quantum electrodynamics, seems to have been directly confirmed through these physical observations, which makes this study and this observation a huge win for quantum mechanics. And because QED is one of the most thoroughly tested theories in physics, here this only confirms its accuracy and its overall success in predicting these very strange effects. With this unusual star, 15,000 light years away from us, basically becoming this high-energy physics laboratory, while at the same time suggesting that neutron stars basically have to be studied just a little bit differently. By confirming that this crystallization is real and seems to actively reshape light as we see it, astronomers can now, for example, use this to possibly map geometries of these stars and locate their hotspots with unprecedented precision. But obviously this also proves that what we call nothingness or vacuum is actually still something. It is a physical medium that can be changed by extreme forces. On that note, well, that's pretty much it. I'm sure there will be more discoveries in the future, but until then, check out previous videos in the description. Thank you for watching, subscribe, come back tomorrow to learn something else. Support the show on Patreon where you can find additional videos without any ads and can DM it directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.